Okay, this chapter is on the periodic table. In order for us to really start to understand the periodic table, we need to understand what an atom is, because an atom is very much a big part of what the periodic table is all about, because everything that's part, or every element that's part of the periodic table, their main component, or what they're made up of, these things called atoms. So we've got a picture here of a blown up picture of an atom, of course. The bulk of the atom, as far as the volume goes, are the electrons. Even though they're teeny, teeny, tiny, the bulk of the mass, though, is going to be your protons and your neutrons. So your protons are the positive ones, and the neutrons are the blue ones, which they have no charge at all. And then electrons are going to have a negative charge. So these are the three things that are consisting in the atom. And then, of course, the nucleus is that central core that contains the protons and the neutrons, and so that's a central part, kind of like the nucleus of the cell is like the brain or the central part of the cell. The nucleus of an atom is that central core, and it has protons and neutrons in the core, and then electrons that just kind of like circle around the outside. And the reason why they have both protons and protons and electrons is those opposite charges, the positive and negative, attract each other, which kind of keeps them all together in the atom. Okay, so here, a little bit more about that structure of the atom. The electrons move within a sphere-shaped region surrounding the nucleus. It's like a three-dimensional thing. It's hard to imagine without actually seeing something that small, because it's almost impossible for me to imagine seeing these things. But they very much are like very three-dimensional in the way that their electrons kind of spin around the outside. Neutrons and protons have about the same amount of mass, but electrons are about 2,000 times less mass than the protons and neutrons. So protons and neutrons are teeny, but 2,000 times less mass than that are your electrons. So that tells you a little bit more. I included this picture over here. And in your book, there's like several more pictures as far as the models of the atom have gone over the years. And I just thought these are kind of interesting. These are kind of your more up-to-date ones. They have some that were pretty old-fashioned that didn't stick around very long. But starting in 1911, they started recognizing that electrons were kind of spinning around the outside instead of just all staying in one like two-dimensional shape kind of stuck on the outside. They recognized that these are kind of going around in very specific orbits around the nucleus, those electrons, those little dots here are the electrons. This is the one that I learned when I was in high school, and it came out in 1913, but it was around for a really long time. And the neutrons weren't discovered yet, so at this point there was, for me, I knew about neutrons. I shouldn't say it that way, because Chadwick model brought in to the Bohr model, it just added neutrons into that. But this is what I learned. I learned this Bohr model, that inside, and then we have these like very specific, they called them layers, I think, or levels. Levels is what they call them, levels. And so at each level they had a certain amount of electrons that could fit in each level, which to a certain extent is still used today. They kind of know how many electrons fit in each level, but this is very two-dimensional as far as how they show it. But this is obviously not what we think of now, because here's our most modern day present model of the electron and protons and neutrons all together. So here's your atom. So Chadwick introduced that neutron. He noticed what the neutron is and recognized why things are heavier, because protons and neutrons together make up a fairly large mass as far as the atom goes. And so here's today's, where we got that cloud of electrons going around, and then their central core of the protons and the neutrons. Now this is interesting stuff, stuff to remember, stuff to kind of start learning, because as you get into high school chemistry, this will be stuff that you'll need to remember. Elements are identified by the number of protons in the nucleus. So when we get to talking about the periodic table, you'll notice there's a number that each one of the elements is known by. And that number represents the amount of protons that are in the nucleus. Now, protons and electrons are the same, but we base it on the number of protons. Okay, so that's why when we talk about what is the atomic number, we're talking about the number of protons. So they're identified that way. So the atomic number is the number of protons in the nucleus. When we get to the periodic table, I'll point that out to you again. I included this one not because it has anything to do with atoms and the elements at this point, but I think this is interesting. This is an image of atoms, basically a bunch of atoms put together. It's made by a scanning tunneling microscope, something you don't have at our school. But this is made by that, and it shows a zigzag chain of the red atoms here They're cesium atoms, and the background of gallium and arsenic atoms, which are blue. And they basically added the colors to them to kind of separate the different types of atoms. But I think if you could see something like those are a bunch of atoms put together there, it's kind of crazy to think about. I thought that was an interesting picture the book included. Okay, one more thing about atoms and elements. In this section, we talk about these things called isotopes. Isotopes are basically atoms with the same number of protons because that's what makes them what type of element they are. So protons cannot differ in a certain element. If I have carbon, which has 6 protons in it, it will always have 6 protons no matter what, and it will always have 6 electrons no matter what. The thing that can change is the number of neutrons, and if it has a different number of neutrons than just 6, which is what carbon should have, we call that an isotope. So the mass is the sum of the protons, neutrons in the nucleus of an isotope. So if we have more neutrons than we do other things, then we can talk about what the different things are. So for instance, this is called carbon-12. That's what carbon-12 should be. It should have 6 protons, 6 neutrons, 6 electrons. Carbon-12 is your normal carbon. We can have carbon-13, which means we have 6 protons and 7 neutrons. We still have 6 electrons and 6 protons, notice, because they have to have protons, and they have to have the same amount of protons and electrons, and 6 means it's carbon. If it has 6, it is carbon. But if we have 7 neutrons, that makes an isotope. It has a differing number of neutrons. And so this makes it carbon-13. Carbon-14, if you remember anything about what we learned about fossils and things like that, carbon-14 is one of the common ones they use to try to figure out ages of fossils. But that's, again, an isotope of carbon. Always has the 6 protons and 6 electrons, but it has a different amount of neutrons, 8. So 8 plus 6 is 14, making it carbon-14. So basically, isotopes are going to have a different number of neutrons in the nucleus than the normal amount that you'd expect, which would be the number of protons, electrons, and neutrons should be the same. But sometimes neutrons, they have more or less than you'd expect, and that makes them isotopes. This is the end of the section. There will be homework posted. There will be reading material posted. And then again, you can either print that homework off, you can do it off of the PowerSchool Learning and take a picture of it and send it to me either way. You can hand it in on one of the hand-in dates. They're also part of a package you can pick up at school if you go in to pick up stuff at school. So a lot of different ways to get the homework for this. Enjoy!